Hello everyone, this is Dr. Hopkins with our next video in the series for 106, Chem 106. We're going to talk about acid-base reactions, or strong acid, strong base reactions. So far, we've been doing reactions with acids and bases where they're always reacting with water. So the question becomes, what happens when an acid, strong acid, reacts with a stronger base than water? Or likewise, we could say what happens when a base reacts with a stronger acid than water? We get a neutralization reaction. So actually here I'm writing out the strong acid dissociation the way we've been doing it, where we have HCl and H2O, gives us H3O plus, and then our spectator is Cl minus. So we really don't even need to write the Cls in this case. So if we, what we've been doing, if we had 0.5 molar HCl, the pH would be 0.301. So what if we add sodium hydroxide to the HCl instead of water? So HCl is a strong acid, sodium hydroxide is a strong base, so we can completely dissociate into H+, and we're going to now at this point, and pretty much for the most of the rest of the course, when we have strong acid, strong base, I'm just going to write them as their H+ or OH-. The spectator ions really don't matter. All they're doing is balancing charge. So we get H+ plus OH- gives us H2O. Or if we were to write our proton as H3O plus OH-, we get H2H2Os. And that, if I'm not mistaken, looks like the inverse, so reverse reactants and products of the autoionization of water. And it turns out if we have an equilibrium that we invert, we also invert the equilibrium constant. So we start out that the H2O to H3O plus and OH- is Kw. So the equilibrium for the H3O plus OH- is 1 over Kw, which is 1 times 10 to the 14. Which is a huge number. It's very large. And so basically what this means is that anytime you have a strong acid, strong base, it's going to react and form all products. There will be no H+ left. There will be no OH- left if there's not excess of one or the other. So we can write that without the equilibrium where we have the arrow for H2O. So starting from that reaction, this, if I'm not mistaken, is just like stoichiometry that you did last semester. If you had a reaction like this, you would do stoichiometry, figure out the number of moles of H+, the number of moles of OH-. Is there something excess? Is there a limiting reactant? And then at the end of that stoichiometry, you would figure out, hey, what is the strongest acid or base left? That's what's going to dictate the pH of my solution. So let's do this process for 10 milliliters of 0.5 molar HCl and 5 milliliters of 0.5 molar sodium hydroxide and figure out the resulting pH. So here we set up our problem. It's going to be a stoichiometry problem, and I'm not going to write the equation just yet because I'm going to write that in kind of a pseudo ice table kind of format with moles. But so we have our moles of H+, so our HCl, we had 0.500 molar, which is moles per liter, and we had 10 milliliters of that. So that was 0.010 liters. So I'm just dividing it by 1,000 and doing that math. So this is 5.00 times 10 to the minus 3. You can't see that very well. And then the moles of OH- was 0.500 moles per liter. See if I can fit this in a little bit better. 0.005 liters, because it was 5 milliliters. And that's 2.5 times 10 to the minus 3 moles. So those are the 2 moles that we react originally. Now let's write our reaction. H+ plus OH-. Both of those are aqueous. I'm skipping that step for right now. This is liquid. We don't really care. So I'm going to kind of write this out because what we have is a limiting reactant problem. And I think you can already figure this out since it's 1-to-1, but we're going to write this because I'm going to use this kind of in future work. So let's see, 5.00 times 10 to the minus 3 moles of H+, and 2.5 times 10 to the minus 3 moles of OH minus. We don't care because H2O is not really going to matter. And so this is limiting. So if we got rid of all of this, we would be left with 0 moles of OH minus. Since it's 1-to-1, we would also get rid of 2.50 times 10 to the minus 3 moles of H plus. But we would be left with 2.50 times 10 to the minus 3 moles of H plus after the reaction. Okay, so what's going to dictate our pH? Excess acid. So our excess acid is what dictates our pH. So pH, remember, is a measure of the concentration. So we need to figure out concentration because this is moles. So our concentration of H plus is 2.50 times 10 to the minus 3 moles. Now how many liters do we have? Well, you'll notice we added 10 and 5 milliliters together. So that's 0.0150 liters. If we divide that out, I think that's 0.166. But then if we do the pH of this, it's negative log, and I didn't write this down, of 2.50 times 10 to the minus 3 over 0.0150. So just do the math automatically. We end up with a pH of 0.778. So you'll notice, remember when we did this math earlier and we added 0.5 molar HCl to water, we ended up with a pH of 0.301. Now we have 0.5 molar HCl reacting with some amount of 0.5 molar sodium hydroxide. The pH has gone up because we added base, but it's still very acidic because we had excess strong acid. So now that we solved the problem where we had excess strong acid at the end, why don't we add 10 milliliters of 0.5 molar HCl to 10 milliliters of 0.5 molar sodium hydroxide. Let's figure out what the pH would be at the end of this reaction. So now we take a look at this problem where we'll work through, and I've already written out where we have the moles of H plus. Actually, the moles of H plus is the same as it was in the previous problem where we had 0.5 molar and 10 milliliters, and we get 5 times 10 to the minus 3. And we add to that moles of OH minus, same concentration, same volume. It's going to be the same moles. So if we were to set this up, and we'll go through this, but we know what's going to happen. So 5.00 times 10 to the minus 3 and 5.00 times 10 to the minus 3. There is no limiting reactant. Both of them are stoichiometrically equivalent. So we have stoichiometric equivalent amounts. So we're going to subtract away that, subtract away that, and lo and behold, we have no excess H plus or OH minus. So what's going to dictate our pH? The pH is our water, right? We still have water. We've created that as a product. So how would we determine the pH if we just have water? Well, we just go back and we're going to go through the exercise. I think most of you know the answer already. It's H3O plus OH minus, right? And now we start with, if we were to set up an ice table, actually let's do it this way, sorry. And this is 0 and 0 plus x and plus x. That doesn't factor in. X and x. And then x squared is equal to 1.0 times 10 to the minus 14, right? Because that's the kW. And that means that x is equal to 1.0 times 10 to the minus 7. And the pH is the negative log of 1.0 times 10 to the minus 7, which means it's 7.0. So when we have neutral, strong acid equals strong base. So moles of strong acid, moles of strong base. And this is the kind of thing you used when you did acid-base titrations last semester. But the pH is now dictated by water itself. Water is the strongest acid and base left. And if that's the case, the pH is 7. And lastly, we're left with our key takeaways from this video. Neutralization reaction, at least between strong acid and strong base, always reacts completely to products, so whatever that might be. And so it's a limiting reaction problem or a limiting reactant problem. The pH of the solution is dictated by whatever's left, right? So what's the strongest acid? What's the strongest base left after the reaction? That dictates our pH. And if we're at the equivalence point where we have equal moles of strong acid, strong base, the pH is the pH of pure water. So until next time.